Hello everyone and welcome back. I am Mr. Cobalt and I'm going to be going over the second problem for thermal heat energy transfer. So in this problem, very similar to the first problem here, you have a block, you're putting in water, but this time they're asking you to solve for the mass of the block because they're not giving that to you, but they do give you the final temperature at thermal equilibrium. So everything is pretty much the same. So I'm going to set it up the exact same way as before. So again, they have to give you the specific heats of the block, the copper block, the copper, and the water. So water is going to be the same as before. So the specific heat of water is going to be equal to 4.18 joules per gram degrees Celsius. Okay, and then for copper, we need to look that up. So for copper, it's going to be 0.385. So copper, the specific heat of copper is equal to 0.385. Again, that's joules per gram degrees Celsius, 0.385. Let me double check to make sure I got that right. 0.385. Okay, good. So once again, the way we're going to set this up is, since this is a heat transfer problem, the heat lost by the system is going to be equal to the heat gained by the surroundings. So you just need to make sure that you got everything that's in the surroundings, everything that's in the system when you're doing that heat transfer. Again, this one is a simple problem where you've only got two things. You've got one thing, the block, which is your system, and you've got the water, which is your surroundings. So you're gonna transfer heat from one thing to another thing. So we'll have 0 is equal to Q. In this case, Q1 we'll say is the water, or we could say the copper. It doesn't matter. So say Q1 is the heat for the water, the heat transfer for the water, and Q2 will be the Q of the copper. Okay, so again, in the same way as before, since we're giving heat capacity, specific heat capacity for both, that tells us that the formula we're going to need to use is Q equals mass times the specific heat capacity times the change in temperature. And then again, the reason that I know that is because specific heat capacity is in joules. The units are joules per gram per degree Celsius. So I want a unit energy. I want an energy unit. So the way I'm going to get that energy unit is by multiplying by a mass and by a temperature change. And so since they give me the heat capacity, the specific heat capacity of both of these, then again, I'm going to replace the Q values with this formula, but I'm going to specify which substance I'm using. So for Q of water again, it's going to be the mass of the water multiplied by the specific heat of the water, and then multiplied by the temperature change. So the temperature change is going to be final temperature of the water. Or in this case, again, the final temperature is going to be the same for both because they're at equilibrium. So that I could just say T sub F minus the initial temperature of the water. Oops, H2O. And then I'm going to add that to the copper. So I'm going to add the copper to that. So that's going to be the mass of the copper times the specific heat of the copper times, and again, TF, final temperature, since they're both at the same final temperature, minus the initial temperature of the copper, since they're going to be at different initial temperatures. And so once again, I have my equation. In this case, I don't know the mass, but I do know the final temperature. So this time I'm going to be looking for the mass of the copper block. So this is what I am going to be looking for here. So again, I plug everything in. So 0 So the mass of the water, in this case, the mass of the water is 95.7. So we have 95.7 grams times the specific heat of water, which is going to be, again, where is it? 4.18 joules per gram degrees Celsius, and then final minus initial temperature. The final temperature is 24.2 degrees Celsius minus the initial temperature of the water, which is 22.7 degrees Celsius. So I've got that done for the water, and now I'm going to do the copper. So the mass of the copper is something I don't know, so that's what I'm looking for. So the mass of the copper multiplied by the specific heat of the copper, which is going to be 0.385 joules per gram degree Celsius. And then, again, multiplied by the final minus initial temperature. So again, the final temperature is the same for both, 24.2 degrees Celsius minus, and then the initial temperature of the copper is going to be 65.4 degrees Celsius. So now I have everything plugged in. So again, all I'm doing is I am going to solve for the missing piece. So again, at this point, I'm just calculating. So I'm going to multiply 95.7 times 4.18 times, and then I have 24.2 minus 22.7 equals, and I get, for this, 0 is equal to 600.039. And again, grams cancel out, Celsius cancels out, so I'm left with joules. So this is joules. And then I do this one, so it's going to be mass of the copper times whatever this comes out to. So that's going to be 0.385 times, again, that's going to be 24.2 minus 65.4 equals, and that's going to be a whopping negative 15.862. And again, this is going to be Celsius cancels out with Celsius, so this is going to be joules per gram. Okay, so now what I'm going to do is I bring one of these to one of the sides, it doesn't matter. So if I bring this one over here, so that's going to be a negative, so I'm going to be negative 600.039 joules is equal to the mass of copper multiplied by negative 15.862 joules per gram. Okay, and then let's go back to our sig figs here, so we know what our sig figs are. So we have 3 sig figs here, 3 sig figs here. Here we are subtracting, so it's decimal place. So the least number decimal place is the last decimal place here. So 1 decimal place. So we're only allowed 1 decimal place in our answer here. So that's going to be 3. And so that's going to be 3 here. So that's going to be 3 sig figs, 3 sig figs. So everything is 3 sig figs. So our last significant figure is that one. Same thing for this one here. So yeah, and we multiplied by 3 here. So we have 3 sig figs here. The least number of decimal places is 3. So this is going to end up having 3 sig figs times 3. So 3 sig figs there. All right, so we have 3 sig figs. We're going to divide. And so as soon as we divide, The joules are going to cancel out because when we divide by this, grams ends up on top. We're dividing by this fraction here. So joules is going to end up canceling out. So if I divide by negative 15.862 joules per gram, I'll have negative 15.862 joules per gram. So I'm dividing by a fraction, so that's going to flip. So my joules are going to end up canceling out, leaving me with grams. So I have 600.039 divided by, or negative 600, divided by negative 15.862 equals, and that gives me a mass. So the mass of copper is equal to 37.8287 grams, but because I have 3 sig figs here, 3 sig figs here, so the least number is 3 sig figs, so I'm going to cut it off at 37.8 grams. So that was the mass of the copper that was thrown into the water. So this is the way that you would do these sorts of problems. These are simple problems because you only have one block and water. But again, it doesn't matter what they throw at you as long as you're keeping track of what's in the surrounding systems. So here we have Q1, Q2, but again, they didn't throw a calorimeter in here, or they could throw a solution in here, or ice being melted in water. So you would have to add those as sources of absorbing heat from the reaction, or gaining heat, or whatever the case may be, or losing heat. So I hope this is helpful. If you like this video, go ahead and like it, share it with your friends. You can hit the notification bell for notifications of other videos. You could subscribe to the channel and make a comment in the comment section. So tell me what you think and let me know if there's anything else you want me to cover. Okay, thank you very much, and I'll see you next time.